both of these carbons, this one and this one, are both electrophilic sites. So we can kind of swap them in as an electrophile for various reactions. The other thing that's special about epoxides is that three-membered ring gives it a lot of strain. So the angle here, this bond angle, is about 60 degrees. That's really small. So you're kind of forcing this molecule into this strained form, which makes it more reactive. So again, we're going to learn more about ethers later, but that's like a really special property of epoxides. Okay, so knowing that this is an electrophile, we can now react this with an organometallic reagent. So I'm going to show phenyl lithium as an example. And again, remember for organometallics, you can sort of think about it as the negative charge being on carbon, like having a lone pair here and a negative charge with a lithium counterion. It's not actually that. There is actually a bond there, but I think that that is helpful to think about because then it becomes more obvious where the reaction is happening. And then we're going to react this with ethylene oxide. Okay, so again, we have these two carbons. They are both electrophilic, so I'm just going to choose to attack the one carbon. It doesn't matter. Our nucleophile is going to attack our electrophile, and we're going to release the ring strain by breaking the carbon-oxygen bond. So this is an SN2 reaction. So it's one step, happens all at once. And our nucleophile is attached to the one carbon, but our oxygen is now attached to the two carbon, or still attached to the two carbon. And then lithium is still our counterion. Okay, so let's note the difference here, right? Because we're breaking this oxygen carbon bond to carbon number 1, the oxygen is still attached to carbon number 2. So the oxygen is attached to carbon number 2, not carbon number 1. Okay, so now we have our alkoxide, right? The negatively charged oxygen. So to make our alcohol, this is why we need that second step where we add in our acidic workup. And that is just going to grab this proton to make an alcohol. Okay, so this is very similar to our organometallic reagent plus an aldehyde or ketone, except for the fact that oxygen is now on the 2 carbon instead of on the 1 carbon. So the driving force of this reaction is that ring strain. This ring strain is released, right? So we go from that angle being about 60 degrees to the more preferred 109 degrees. And so by releasing that ring strain and making those bond angles be happier, that is the driving force of this reaction. Okay, we see how those are very similar, but a little bit different. Yeah. Yeah, so benzene double bonds are not very nucleophilic, right? So remember EAS, we had to make a really, really strong electrophile in order to get it to go. Whereas this is a carbon that is like really negative, right? Like it has a lot of electron density. So that's much more nucleophilic. Like aromatic double bonds are just not super nucleophilic. They're a little bit because we can make EAS go, but we have to like work to get EAS to go. Whereas this is going to react really quickly. Yeah, great question. Other questions on that? Okay, let's look at an example. So this time we'll use a magnesium chloride reagent. So I will take some sort of alkyl magnesium chloride. It doesn't matter, any organometallic. And then we mix it in with our ethylene oxide, ReO. Okay, so this time I'm not going to draw out the negatively charged version. I'm going to draw my arrow from this carbon metal bond, right? That's the electron density that's going out and attacking things. Nucleophile attacks electrophile, break the weakest bond. SN2 reaction. Nucleophile attacks electrophile, break the weakest bond. So that means that we have our nucleophile that should be attached to the 1 carbon, then we have a 2 carbon, and then we have our oxygen, which gained electron density, so it should now be negatively charged. Our counter ion is now magnesium chloride. That whole thing is positive. So now, just to get our alcohol, we just need to quench the charge by doing an acidic workup. So again, important to write that this is a second step. Second step, very important. Just add in a little bit of acid, and then that alkoxide will grab the proton to make our alcohol. I highly recommend that you number your carbons. It's very easy to get these mixed up, okay? But if the oxygen ends up 2 carbons away from your nucleophile, it's ethylene oxide. If it's 1 carbon away from your nucleophile, it's going to be a carbonyl compound, okay? Well, let's do a chiming question to see if that's making sense. We're going to compare this reaction to the one of organometallic reagents with carbonyls. So here's a thinking backwards, right? So this is a proposed starting materials type question. So I want you to propose the starting materials for the following reaction. So I'm giving you the product, okay? I'm giving you that there's a second step for the aqueous acidic workup, and I'm giving you 3 sets of potential organometallic compounds and electrophiles, and I want you to tell me which ones will give the product shown. So we're going to give you a couple minutes to think about this. Feel free to chat with your neighbors. There can be more than one correct answer. Maybe 10 more seconds to get in your answers. Let's see what we got. Great, excellent. Okay, this is awesome. I'm actually pleasantly surprised that most people got that. That's awesome. This is really challenging, right? They're very similar. They're a little bit fiddly, but most people are getting it. So these have to be done with the carbonyl compounds as our electrophile because the alcohol is on the carbon directly next to our nucleophile. So let's draw that out real quick to make sure everybody is on the same page. So you were asked for the starting materials to make this compound right here. Okay, so let's remind ourselves that this can be abbreviated as a phenyl, PH, because it's easier to draw. So I'm going to abbreviate that. So the first set was phenolithium and ethylene oxide. So if we were to draw out what we would get from that, we would get the alcohol on the 2 carbon, whereas here it's on the 1 carbon. So this one does not work, right? Because you would get the wrong connectivity, right? The oxygen is on the wrong carbon. It's on the 2 instead of on the 1. The next one was phenolithium and acetaldehyde is what that's called. So if we draw out what we get for this, you would get phenyl, 1, 2. Now our oxygen is attached to the 1 carbon. So that's correct. That is what we want. And then the last one just flipped around which substituent was on the organometallic and which was on our carbonyl compound. But this still works because if we draw what we get here, our organometallic attacks that carbonyl carbon. Our methyl group comes from the organometallic, but it doesn't matter. Next to the phenyl, it's still 1. It's on the 1 carbon. So this is the same product. The only thing that's different about the last 2 sets is that which bond we made. So we either made the bond on the left or we made the bond on the right. But they make the same product, so you can do it either way. Questions on that? Make sense? Okay. All right, so that's that reaction. So let's do our quick review of chapter 5 reactions with alcohols. So what can you do with alcohols now that you can make them, right? So we just showed you a bunch of ways to make them. So now let's do a bit of a review. So this is actually 16.6 in the book, which is a review of chapter 5. So a review of reactions with alcohols. Okay, so you've learned a lot of reactions with alcohols already. So one of the big ones is 2 alkyl halides. Remember, alkyl halides have this kind of general form where X is a halide. So usually it's going to be like chlorine or bromine, but it could be fluorine or iodine. And the reason that these are important is because they're good electrophiles. So you can turn an alcohol into a good electrophile. And you learn lots of different ways to do this. So if you have your alcohol, you could just use a mineral acid, HX, to turn it into an alkyl halide, where X is chlorine, bromine, or iodine. So that's sort of the generic works for all of them kind of reaction. But you also learn some specific ones. So you could also have an alcohol and react it with thionyl chloride, which is SOCl2, thionyl chloride, and that will give you the alkyl chloride specifically. Or you could react this with phosphorus tribromide, PBr3, and that will give you the alkyl bromide. So all of those, just different options to get you to an alkyl halide. Okay. So that's a way to get to a good electrophile. Another common reaction is E1. So let's do maybe the product from our timing question, this guy. If you expose this to acid and heat, so this triangle here means heat, you will eliminate, so you eliminate water to generate an alkene and water. And the reason that this happens is based off of whether you can make a stable carbocation. So first, you would protonate your alcohol to make it a better leaving group. Then the leaving group leaves by itself, and we generate this stable carbocation. We have water. And then to get to the alkene, our water pulls off an adjacent proton and we form the double bond. So this is based off of that carbocation stability. Okay, so here we made a secondary benzylic carbocation, very, very stable. This is going to want to go pretty quickly. Okay, so that's E1, right? And it's multiple steps. This is not E2, it's E1. So you make a good leaving group, it leaves, you form a carbocation, and then you pull off an adjacent proton. That's E1. Okay, the last one that we want to review is called tosylation. So here, again, we have an alcohol. You react with a reagent called tosyl chloride, which is kind of a weird looking reagent. But essentially what happens is that you take the proton from the alcohol and the chloride from the tosyl chloride to make HCl, and you put the other things together. So I'm going to have my alcohol now attached to my sulfur, like so. Probably should have drawn that tosyl chloride in the opposite direction, but it is what it is. So we did that, and we joined, and we got HCl as our byproduct. So this group right here is called a tosylate. It's abbreviated as OTS, so capital O, capital T, little s. Tosylate. This is a really good leaving group. So this is another way of converting an alcohol into a really good leaving group. So that is what it is used for. Okay, so those are reactions that you previously learned that might be useful in, for example, designing a multi-step synthesis or something. So these are good reactions to know, and E1 is going to come back in a couple minutes. All right, so now let's go on to our next learning objective, which is 16H, which is the 4 Ps for the formation of ethers from 2 primary alcohols, which is section 16.7. So here's where that primary alcohol comes in, right? So the overall reaction that we're talking about is that we have a primary alcohol. I'm drawing it twice so that I can color code it as both the nucleophile and the electrophile. We add acid, we add heat, and we get an ether. So this is called an ether. We have that carbon, oxygen, carbon, carbon, oxygen, carbon. That is an ether. And we got water as our byproduct. Okay, so our primary alcohol is our nucleophile and it's our electrophile. So this is a primary alcohol reacting with itself. So that's kind of crazy. How do we have a molecule that can be both the nucleophile and the electrophile in the reaction? Let's look at the mechanism. So the first thing that we need to recognize is that OH minus is a bad leaving group. It can occasionally happen, but usually not. It's a bad leaving group. So we want to make a better leaving group. So under acidic conditions, just like in E1 that we just reviewed, you can protonate an alcohol to make it a better leaving group. So whatever our proton source is, say here's just our acid. This is going to be a proton transfer where we grab a proton from our alcohol. Like so. And by protonating that alcohol, we have now made a much better leaving group. It's a positively charged oxygen now, so when it leaves, it will be neutral. So that's okay. So now that we have a better leaving group, hopefully it's more obvious that our electrophilic site is the carbon attached to your leaving group, right? Whenever you have a leaving group, the carbon attached to your leaving group is the electrophilic site. So we can now bring in our second equivalent of our alcohol. The lone pairs on the oxygen is the nucleophilic part. That's where the electron density is. So we've identified our nucleophile. We've identified our electrophile, right? Our electrophilic site. Nucleophile attacks electrophile, break the weakest bond. This is another SN2 reaction. All happens in one step. Nucleophile attacks electrophile, break the weakest bond. Okay, so from there, we get our nucleophile has replaced the leaving group. It is still protonated. We lost water. And then to get to our final ether, we just need to deprotonate using our water to regenerate our acid catalyst. And that will give us our ether. Okay, so it's essentially a proton transfer, an SN2 reaction, and then another proton transfer. That's all this reaction is. It's an SN2 reaction where you need to make a slightly better leaving group at the beginning and then quench the positive charge at the end. Questions? Yes. Yeah, so I just like basically combined the acid catalyst and the water, right? Because we started with an acid catalyst, so we regenerated an acid catalyst at the end. So water is the byproduct of the reaction, but you are also using the water to regenerate your catalyst. Yep, good question. Excuse me? Why do you need heat? Great question. So even though you are making a stronger leaving group, it's still not the best leaving group. And so you need heat to just like push it a little bit more. Yep, great question. Other questions? All right, let's look at some examples, or actually, why is this only primary, right? So we specified this must be primary, so why is that? This is very, very important. You can't just do this with any alcohol. So why only primary? So I said that E1 is going to come back. That's because secondary and tertiary alcohols will do E1 instead. So because that first step of the mechanism is the same, you're kind of set up for both. So again, acid, heat. First, we protonate our alcohol, right? So we've made a better leaving group. So from here, where our electrophilic site would be, right, the carbon attached to our leaving group, is very sterically hindered, right? So if you recall, if you have a very sterically hindered electrophilic site, you cannot do SN2. So this reaction is supposed to be an SN2 reaction, and it would give you an ether that looks like this, but this is not going to happen. This is not favored because this is sterically hindered. Okay, so you don't make this product. SN2 is very slow. So we say that this is disfavored. So instead, we can do E1, where the leaving group that we made just leaves by itself, and we generate a carbocation, right? And because secondary and tertiary alcohols will give secondary and tertiary carbocations, which are more stable than primary, it favors E1. Okay, and then from there, we just need our water to come in, grab the adjacent proton, quench the positive charge to make our alkene, and regenerate our catalyst. Okay. So it's based off of the stability of that carbocation versus the rate of SN2. So you can really only do this reaction with primary alcohols. Otherwise, it just does E1 instead. Okay. So that's kind of like the big important thing about this reaction. It must be primary alcohol. So make sure you check that if you want to use it. Questions? Okay. So every example I've shown you so far has been intermolecular. It has been two different alcohol molecules that come together to form one ether. That does not have to be the case. So let's look at the intramolecular example. So the two alcohols can be attached to one another. So we would call that a diol. So one molecule with two alcohols is a diol, two alcohols. Okay, so this is going to be the intramolecular reaction. So intramolecular means within one molecule. Okay, so it's the exact same reaction. Don't be confused that it's in one molecule. It's the exact same reaction. It just looks a little different. So I am going to draw a diol. Okay, we're going to number our carbons because this can get tricky. 3, 4, 5. Okay, so this is our diol, two alcohols. Okay. And I'm going to arbitrarily choose one of these alcohols to be my nucleophilic one. So I'm going to say this one on the left. So the lone pairs there are going to be our nucleophilic one. And then I'm going to arbitrarily choose the one on the right to be the electrophilic one. So this side is going to be the electrophilic one. So the reaction is the same. We need to make a better leaving group on the electrophile side. So let's do that. So we have our acid, we have our heat. Our electrophilic side is going to grab that proton. One, two, three, four, five. So I protonated the electrophilic side, right? I have made my leaving group. Let's number our carbons again. 3, 4, 5. Okay, I've made a leaving group. So we should be able to identify our electrophilic site, which is attached to the leaving group. So that should be carbon 5 right here. Yeah, the carbon attached to the leaving group. That's your electrophile. Our nucleophile is still the lone pairs on our nucleophilic alcohol. So we've identified our nucleophile right here. We've identified our electrophile right here. Nucleophile attacks electrophile, leaving group leaves. Break the weakest bond, right? SN2 reaction. Nucleophile attacks electrophile, break the weakest bond. Okay. So this is our SN2 reaction. All right, so here's the tricky part. Here's the tricky part for intramolecular reactions. You are forming a ring. So what I do is I look at how many things are in the ring. So I'm going to have this oxygen is going to be in the ring because I'm forming a new bond to it. And then there's 1, 2, 3, 4, 5 carbons in the ring. So 5 carbons, 1 oxygen means 6 atoms in the ring. So it's going to be a 6-membered ring. Okay, so that's what I'm going to draw first. I'm going to draw my oxygen and 5 carbons in a ring, like so. Then I'm going to number my carbons so that I don't lose them. 1, 2, 3, 4, 5. Okay, so I just double check. I've got my 5 carbons. I've got my oxygen. That was the nucleophile in the ring. Okay, so then what else do we have? Well, the oxygen that's in the ring still has a proton on it. So that must make it positively charged. And then we lost water. So there should be water over here as well. So that's the hard part of intramolecular reactions. It's like the only weird part is that we have to make this ring. Then we just pull off that proton, quench the positive charge to get to our final product. Okay, so this blue oxygen is the one that's in the ring. This right here is that ether functional group. So this is called tetrahydropyran is the name of that molecule. Might be similar to tetrahydrofuran, THF, the solvent. So my challenge to you would be to go backwards from THF. So a 5-membered ring with 1, 2, 3, 4 carbons. Go backwards. What is the diol that you need in order to make this product? So I will include the answer in my notes. Yes. Mm-hmm. It depends on the reaction, right? So like for NAS, it was the carbon attached to the leaving group. In SN2, it's the carbon attached to the leaving group. In a carbonyl, it is the carbonyl carbon. Yeah, it's like whatever is the most delta positive site is the electrophilic site, but it depends on the reaction. Correct. Yeah. Okay. In the last few minutes, we're going to do our last learning objective, which is to show how you can put some of these things together. So learning objective 16I, design a multi-step synthesis using reactions of alcohols. So if we were to give you, start with this chlorobenzene, multiple steps to get to this ether. How would you do it? So this is a little tricky. There are multiple steps here. So when you're approaching multi-step synthesis, go backwards. It is so much easier to go backwards because there's so many reactions that you can do that you don't necessarily know if they're going to be productive to get to the product that you want. But if you start at the product that you want and you start working backwards, it's much easier. So we're going to do that. We're first going to recognize that we have an ether here, right? And we realize when we make an ether, like we just talked about, we break the bond next to one side of the oxygen. So we're going to break the bond over here, for example. What does that give us? That gives us an alcohol on this side and an alcohol on this side. So that's one step back. I could make this ether from this alcohol. These are the same. That's great. Symmetrical molecules makes our life easier. Also, these alcohols are primary. So that's great. This reaction works because it would be two primary alcohols forming an ether, right? Now we can recognize, I know that I have this aromatic ring in my starting material. So that's over here, right? And then I have an alcohol on the 2 carbon away from that group. So I should be able to do a ring opening with ethylene oxide. So if I have my ethylene oxide and some organometallic reagent, so say magnesium chloride, I can make this alcohol because I can break it at this bond, right? And the alcohol ends up at the 2 carbon. So that's ethylene oxide, not a carbonyl, must be ethylene oxide. And then we can make this organometallic reagent from that chlorobenzene. So these are all reactions that you know, okay? And then for multi-step synthesis, you would write it in the forward direction to show each of those steps in sequence, which again, I will do and post with the notes. But thank you. That is all I have for you today. Good job. And we'll continue with chapter 16 on Friday.